What kind of maps do autonomous robots need to navigate? Imagine a robot exploring a busy warehouse or a complex city street. How does it know where to go and what to avoid? The secret lies in the maps it uses. Different maps help robots understand their surroundings and move safely and efficiently. First, there are metric maps. These maps give precise measurements of the environment. They show exact positions, distances, and angles. Robots use metric maps to localize themselves accurately and plan paths in tight spaces. For example, indoor robots need these maps to avoid bumping into furniture or walls. These maps are often created as grids or three-dimensional models. They are essential when high precision is needed, like in factories or laboratories. Next, topological maps focus on how different places connect. Instead of exact measurements, they show landmarks and pathways as a network of nodes and links. Think of it like a subway map, where stations are nodes and tracks are links. Robots use these maps to quickly decide how to move from one area to another, especially in large or complicated environments. They are less detailed but very efficient for navigation decisions. Then, there are topometric maps, which combine the best of both worlds. They include precise location data along with the connectivity information. This makes navigation more flexible and reliable. Robots can know exactly where they are and how different areas relate to each other. This type of map is useful in dynamic environments where things change often. Semantic maps add another layer of understanding. They label objects and surfaces, like chairs, doors, or walls. This helps robots interpret what they see and decide what to do. For example, a robot can recognize a chair and avoid it or use it as a landmark. These maps are especially helpful in environments where understanding the context matters. Occupancy grid maps are widely used for obstacle detection. They divide the space into small cells, marking each as free, occupied, or unknown based on sensor data. Costmaps build on this idea by assigning costs to cells, guiding robots to choose safer or quicker routes. These maps are vital for real-time obstacle avoidance and path planning. An emerging type is visual language maps, which combine visual data with natural language instructions. They allow robots to understand commands like move 3 meters to the right of the chair. These maps are adaptable and can be shared among different robots, making teamwork easier. Lastly, SLAM maps are created using simultaneous localization and mapping techniques. Robots build these maps while tracking their own position in real time. They use sensors like laser scanners or cameras. Visual SLAM relies on cameras to identify environmental features, while laser SLAM uses lasers for highly accurate mapping. These maps are crucial in unknown or changing environments. In real-world applications, these maps help robots plan paths, localize themselves, avoid obstacles, and follow verbal commands. The choice of map depends on the environment, sensors, and tasks. Combining different maps allows autonomous systems to navigate smoothly in many settings. So, whether it is a warehouse, a city, or a home, the right maps make autonomous robots capable of moving confidently and safely.